We'll start this video off with a definition, but then we'll move to some examples. So the third law of thermodynamics, remember the second law was the entropy was always increasing. Now the third law is that the entropy of a perfect crystal at 0 Kelvin is 0. Now perfect crystal is not possible because nothing is ever really perfect or perfectly arranged. But if it was, and it was at absolute 0, it would have no entropy at all. So that basically describes that there is no way to not have any kind of entropy. Everything has some entropy. And that we can actually find that the entropy of the reaction is the entropy of the products, the sum of the entropy of the products minus the sum of the entropy of the reactants. Now remember, this 0 up here means that it's the standard entropy. Okay, so that's what the 0 means, is standard. Right. So in this example, given the following standard molar entropies, calculate the delta S standard for the reaction. Aluminum magnesium oxide yields magnesium plus aluminum oxide. We've been given our standard entropies, so all we really have to do is apply the equation before, where we will just take, we will find the standard molar enthalpies for this reaction, and then set it equal to the sum of the products. So 3, because remember there was a 3 here for the coefficient, 3 times 33 plus 51. Where's the 51? Yeah. So here is the magnesium and the aluminum oxide. Here are my products, and then I subtract it by my reactants. And remember your coefficients right here. Your coefficients need to multiply by the actual standard enthalpies. Take the sum of them, find your answer, and this is the enthalpy of the reaction. Entropy of the reaction. Now that we know this, the units for entropy are going to be joules per Kelvin mole of the reaction. So joules per Kelvin mole. You might want to commit this to memory because this is helpful to be able to work the equation later. Also notice that this is in joules, okay? That'll be important in just a second. The standard free energy change is the change in free energy that occurs in the reactants in their standard states are converted to products in their standard states. So this is basically the same thing as the equation before, except now we're talking about the Gibbs free energy. So the Gibbs free the standard Gibbs free energy change in standard Gibbs free energy, that's a mouthful, for a free element in its standard state is 0. It's a lot of definitions to try to memorize, but it makes more sense in a mathematical equation. So if we have this given reaction here, and we have given the equation of dinitrogen tetroxide yields 2 NO2 molecules, both in the gas state, and the following data here of our standard Gibbs energies of each one of these, we will just basically apply the same equation, where we'll take our coefficient and multiply it by the products. The products is right here, and then subtract it by the reactants to get our final answer. Now notice that the units for Gibbs free energy is kilojoules per mole, and now this one is going to be in kilojoules. Okay, so you need to be really careful about which joules or kilojoules, because that could trip you up and you could be off by a power of 10. So please be careful about kilojoules or joules. So when we, like I said before, whenever we get this equation here, that will be on your formula chart, it's called the Gibbs-Helmholtz equation. and it's very, very nice to have there and be able to try to work your units. Now remember, your units here were joules per Kelvin mole. Uh, well, we'll go ahead and write that. Your units here were J divided by K MOL, and my units here were kilojoules per mole, and my units here were kilojoules per mole. You remember that from the previous chapter. So you're going to run into some problems if you don't remember to convert joules to kilojoules. So here's our equation. For the given reaction and the following information, calculate delta G at 25 degrees Celsius. So we have a constant temperature. That's good. So constant temperature here. Okay. And then we have our reaction. It has coefficients in it. I noticed that it is lead oxide as a solid plus sulfur dioxide as a gas, and then yields lead sulfide as a solid, and then yields oxygen as a gas. So and then we have our enthalpies here in all of our reactants, all of our elements in the equation, or all the things that make up the equation, and then I have all of our entropies here. So I have enthalpies and entropies. So first ask yourself, why is this one blank? Well, that's because oxygen is blank, and then that's because it is an element, or considered an actual elemental molecule. So that one will be 0. We'll just write a 0 right there. Let's separate the reactants, and then our products here. Okay. So you guys remember Hess's law from the beginning, where if we now just need to take all the entropies here, the enthalpies, sorry, and then multiply them by our coefficients. So 2 times negative 100 plus 3 times 0, and then subtract it by the enthalpies of my reactants. So 2, because 2 for my coefficient times negative 218 plus 2 times negative 297 will now yield 830 kilojoules per mole. That's my standard enthalpy for the reaction. Okay, so that's why it's kilojoules per mole of reaction. Now notice that this is, now when we do the next part, notice that this is going to be, our next units are going to be in joules. So you got to be careful, like I told you. We'll apply the same similar step, just like we did before, where we're basically just going to substitute our entropies now. So 2 times 91, that's the 91 right there. And then 3 times 205, minus 2 times 70, and then plus 2 times 248 will now equal 161 joules per Kelvin mole of reaction. That's my standard enthalpy of reaction, standard entropy of reaction. So now apply the Gibbs-Helmholtz equation, and it gave us the temperature. We found delta H and we found delta S, which now will allow us to find the Gibbs free energy, the standard Gibbs free energy of the reaction. That would be delta G standard. So I'm sorry I covered that up, but delta G standard will be down at the bottom of the screen. Just remember when you do these, guys, is that it's just like Hess's law, where we'll just apply the same little thing. So just like I did before in the previous slide, you can apply the same concept of Hess's law as you did before. That's going to be it. All right, thank y'all.